Okay, folks, so hopefully everyone can see the presentation deck. Yes, thanks for the introduction, Julietta. So yeah, I'm Peter, I'm the General Manager of NIAS, and the first thing you'll notice on my starting screen, it doesn't say NIAS, it says AMIC. So I want to give an introduction at the very start to AMIC, which is our new centre, just for a few minutes before we get into biocomposites. So AMIC, the Advanced Manufacturing and Innovation Centre, is part of what we have in Northern Ireland and the UK called a City Deals. And this is a once in a generation investment into a region in the UK to accelerate economic growth in that region for industry in an inclusive and sustainable way. In total, there's a £1 billion investment over 10 years. Into the Belfast region city deal, and that comes into 5 different centres. There's 2 in healthcare, 1 in digital film, 1 in cyber technologies, and the 5th one is advanced manufacturing, which is just ourselves. So it's quite a lot of money over the next 10 years. But what that means for us is, well, NIAS, we've been here for 10 years, 12 years, apologies, 10 years, and NIAS traditionally was a centre where the 2 schools, one from Ulster University and the School of Mechanical and Aero from Queen's University, would work with industry in an environment to undertake R&D. What we have AMIC now coming through is a new centre. It's not to replace that university engagement, it's to supplement that. We will be based over 2 centres, the one on the right hand side existing, where I'm sitting right now with beautiful views over Belfast Lough, and that's going to be the NIAS Centre. And our focus is going to be on composite manufacturing, material characterisation. We're part of the Net Zero Park in Belfast Harbour, which means if we're going to have green technologies, let's say green fuel sources such as a hydrogen blend coming into power factories, it's probably going to come into this area first, so we're very well located. We are a partnership between Queen's University and Ulster University, and we also work very closely with the National Composite Centre in Bristol, as well as the wider HVMC. So that centre exists today. Part of that city deal is also going to create a new Factory of the Future, very original name. Factory of the Future is going to be a 10,000 square metre facility just on the outskirts of Belfast, with the focus on prototyping, verification, digital, photonics. It's everything that's basically not composites and polymers. Our focus is going to be TRL 4 through to 6. It's not the discovery of new technologies, it's about applying those technologies in an industrial setting and de-risking those. And we will work very closely with the 2 universities and other universities in AMIC pipeline, and that's by developing those new technologies and pulling them through, and also we'll identify challenges which is not for us to answer, they're too immature, and we'll move move the technologies through to the universities to do more fundamental research to develop them. And skills will be a big part of what we do as well. So working together with the universities will be critical in developing curriculums. So AMIC's going to be broken into 4 different areas. First of all, smart design. We then have digital, smart nano being photonics. So we make about a third or a half of the world's computer chip readers in Northern Ireland, a company called Seagate. And then sustainable composites and polymers. If we look at our membership base here, we have Spirit Aerosystems, we have Collins Aerospace, we have Thales Defence, we have some big players in composites and polymers. So that's the 4 areas which we will focus in. Our AMIC offer, it's about de-risking innovation and new technology and product introduction, giving companies access to equipment which they need to develop technology, work within the UK and Republic of Ireland ecosystem to develop that world-class capability. And also the last thing is very important is about test bedding technologies. It's not just developing them and leaving them in a report, it's about living and breathing the technologies in a system and being able to adapt that system to industrial scenarios. Our strategic themes, very sustainable focused, so low carbon, resilient, secure supply chain clusters, and that's where the biomaterials starts to come into that. Compression of new product introduction cycles. I look back at Airbus A220, and we really started the development of the resin transfer and fusion technologies back in the 90s, but specifically onto the wing program was around 2007, 2008, and that took 7 years to bring that into first product cycle in 2013, 2014. So how do we compress that by using digital twins? How do we do conceptual design faster? Because more constraints now. We're not just looking at design for manufacture and design for cost. We're now looking for design for sustainability, design for recyclability. So there's a lot more influencers which we need to bring into the conceptual design phase. So how do we do that faster? And then hydrogen is a big theme here. In Northern Ireland in particular, we have a lot of wind power. We produce more wind power at night time than what we need to sustain our nighttime demand. So we have a surplus. So you either turn the wind turbines off, or you store up that wind power in the form of hydrogen, and then bring it down and power our transport sector. And that's already being done with some of our bus network here in Belfast. So looking specifically at composites, so we've been working very closely. The joys of being a new centre, we can start from scratch. We don't have any baggage to bring with us. So we've done extensive road mapping with our Northern Ireland companies, see what are their requirements for the future, and what's their drivers, and what type of technologies will they need to invest in the future, and where will they need our help. But we also looked at that on the UK landscape. So looking at what technologies will we use to satisfy local companies, but also where do we sit within the UK landscape and further beyond as well, hoping to have some niche capabilities to complement the wider high-value manufacturing catapult centres in the UK. So we settled out on these 6 main themes down the right-hand side. I'm not going to go into them too much. What's important is that cross-cutting across those is 2 themes. First one is digital engineering. Digital is everywhere. It needs to be in everything that we do, every new machine which we bring in, every technology. We need to start creating those digital footprints and data capture, those birth certificates. We need to understand everything that's going on with our process and use digital for that. And sustainability. Sustainability is everywhere. That's what I want to talk about a little bit more. So consciousness is a thermoplastics committee. Where do we sit? So I'm getting a little bit of feedback off someone's microphone there. If you could turn it on to mute. So this is going to be a broad sweep introduction to biomaterials. Is there a biomaterial thermoplastic solution for aerospace today? No, there's not. But there's quite I would say it's a TRL4 technology. We know a lot about it, but how do we apply this now into production within different sectors? So sustainable composites, very strong theme within AMIC composites. So we have a biocomposites focus, which we're going to talk about today. Using this, we need to develop technology using carbon negative natural materials as a feedstock and our lightweight, low embedded carbon recyclable composites. We also have a focus on circular economy. So that's for thermoset composites, and that could be wind turbines, it could be aircraft wings, skins and spars, recycling of thermoplastic injection molded product or continuous thermoplastic products, and reuse of aerospace dry fibre. We have a large source of dry fibre waste in Belfast from the Airbus factory. And then factory test bed. I mentioned about replacing natural gas with hydrogen. We're a perfect centre to look at test bedding that and then sharing our learnings with industry. So why is this important? Why are we even talking about biomaterials? What's changed? There was a lot of work done about 4 years ago, 5 years ago now in 2018, looked at potential uses for natural fibre composites, and they're actually quite limited. because at the time everyone was thinking about multi-material systems. How do we lightweight a product? Nobody was thinking about, very few companies were thinking about sustainability. What do you do at end of life, and what's the carbon footprint of the product? A few things have changed since then. Public perception of the importance of carbon footprint of the environment, but that's mainly manifest then through government legislation. So in the UK, the drive to be net zero by 2050. Now, Zurich might change that soon. I don't know, because it is a very ambitious target, but it's a target none same. So we look at the UK. We follow down the light green path. Let me see my cursor. That's the current trend. Sorry, that's the historical trends since 1990 up to 2020. So there has been a reduction. Not dark green is if we do nothing. Okay. But if we want to stay on track, the purple line is what we need to do. Okay, so when we look at domestic is about 27% of that. Industry, 37%, and transport is 36%. So we think about the transportation, our vehicles going about, and also then how do we build those vehicles? How do we generate our wind using wind turbines? Ironic that we make them using non-recyclable materials. And how do we build our homes today? We use a lot of concrete, and concrete is very carbon intensive process. But I look specifically now into Northern Ireland. Our carbon emissions in Northern Ireland, where do they come from? So, and this is a big driver for biomaterials. The first one is actually agriculture. We have one of the highest CO2 outputs for agriculture, certainly in the UK and possibly in Europe. That is driven by the fact that we have a lot of cattle farming. We have a lot of beef, we have a lot of lamb, we have a lot of dairy, and animals create a lot of gases, and those gases go into the atmosphere and contribute to our CO2 emissions. And our farming industry is actually under threat from particularly EU legislation and UK legislation. Do something about it, or we'll have to cut back and the amount of farming which we do, which is a huge threat for us because that's one of our biggest industries. Then we also look at transport sector. It takes a drop down. It's the second biggest contributor. And then we also have buildings. So buildings and our buildings and environment, business and industrial, it's the same, and energy. The reason I pulled this up is that when we look at composites, and we look at our manufacturing sectors, if we look at that in isolation, we can only solve one part of the problem. There's actually many problems which we can solve together. So that what we've been looking at is working with other sectors, not just composites, but with textiles, with energy, with farming, to look at this as a bigger problem that we are part of the solution of. So if we want to decarbonize, two strategies currently within manufacturing sector. First one is to amortize your embedded carbon in a true circular economy. So you take the hit once, you manufacture, you bring materials in, that you manufacture them, their materials and the parts are manufactured with a dirty process, and then you put them through their in-service life. Traditionally, they go to the scrapyard, and you go back to the start again. You go and you're constantly bringing in new materials and taking a large CO2 hit. One of the strategies is to look at end of life, so recycling. So from a carbon footprint perspective, yes, you've got a large hit here, but then you bring that into waste collection. You can reclaim it. You can bring out the fiber and resin, and we've got processes to do that. You've got solvolysis, pyrolysis, and then new processes like pressolysis, which is a decom process using pressurized steam. And what it can do, in theory, it's being proven out at the minute, is it strips the resin back to the monomer. So the fiber is left pretty much untouched. It's not damaged from what they found in their research and their development. And you recover the resin. The process breaks the resins down into the monomer level. What they've discovered now is there might be something they can do with that sludge, because the sludge that comes off this is full of monomers. So how can we put those back into resin systems again? You then take those fiber, potentially in the future the resin, reconstitute material, and then you put it back into a new manufacturing process, back into service, and goes through this several times. So you're amortizing the carbon footprint of the initial manufacturing over several cycles. So it has an effect of reducing the carbon footprint. So that's one strategy. But as every time you do this process, you need energy in this process, so it is not going to solve the problem. Second strategy then is to grow your materials and not manufacture them. So I've used the example of hemp in this case. So industrial hemp, and it's been around for centuries. We used to be in Belfast in Northern Ireland, a world centre of excellence for sails and ropes for the maritime industry. That's what we were known for. In the 1960s, it started to degrade off, especially with the growth of cannabis and cannabis coming through legislation, and a large misconception between the difference between cannabis and industrial hemp. They're the same family, they have the same name, but they're actually very different products. One has THC, the other does not when you grow it. We also have flax and jute, but whenever we grow a hectare of hemp, industrial hemp, we sequester 22 tons of CO2. So we're taking CO2 out of the air. Forget about all these big complex carbon inversion systems, which cost hundreds of millions and may or may not work to take carbon out of the air. Just grow biomaterials and we can solve this problem. In terms of the scale of decarbonisation, I think the figures are right, if we grew industrial hemp on 21% of our free land, which we have available, so available lands in Northern Ireland, we can decarbonise the entire agricultural industry just by growing hemp on 1/5 of the land which we have. And then there's lots of things which we can do with that. So look at that natural fibre supply chain. What does that look like? What does a natural fibre supply chain look like in an environment? What do we need to build? Well, it starts off with the farming side. There's about seed selection. There's not one type of hemp or flax seed. There's tens of thousands, and we can not genetically modify, but genetically select those for our soils and our climates. We have the plant growth phase, harvesting, and then retting. And retting is actually very important on the fibre quality which we get out. Retting, basically you wet the plant and you let the nature break the plant down, which allows you to strip the fibre out from the rest of the herd, which we don't need. But that retting has a big effect on the fibre properties, which we're trying to establish at the minute. We want fibre out of this, then we need to go through a thing called decortication. That basically breaks it down. In centuries in the past, they would have had big beating hammers and sticks to break down the fibre. Well, now we've got plants which can do that. We then need to spin the fibre into continuous yarn. We need to size it, and then we need to weave it. Then we come into the fabrication side, which most of us are probably more familiar with. If we're going down thermoseparate, you need to design the part and design it for natural fibres and for biocomposites. You have preforming, you have infusion, ideally with a bioresin, which has also got its maturity challenges, and then cure. Or if you're going down the thermoplastic route, that polymer blending and injection molding. They're just two examples. We all know that there's dozens of processes, both for thermoset and thermoplastic. And then you've the end use, that performance advantage. Okay, can we get a performance advantage out of natural fibre composites? It's not going to be on strength and stiffness, not compared to carbon, but is there noise attenuation, vibration dampening? There's a cost advantage. Can we make it cheaper than carbon parts or glass components? There's the LCA advantage, which is the big driver for this. And then we take that product to market. So when we look at natural fibres, which we grow, I'm really going to focus in on hemp here. So flax has about 3 or 4 different uses. Usually it goes into textiles, and then it can go into, we know it's available for composites today. Obviously linen is made from flax, and that's a big end use. But we think about hemp has actually a lot more uses. So we'll consider both those fibres together, which we can grow in our lands here in Northern Ireland. We're not as good at growing jute. We don't have the right environment for it. But we can go into textiles. From textiles, we can make fabrics for composites, or we can make clothing, we can make seating. We can go into low carbon footprint biocomposites. We can use it as a filler with an injection molded composite or injection molded thermoplastic granules feedstock, again with a low carbon footprint. They're really the three composite focused areas. But if we were to just try and solve this problem for composite sector, we're going to have a problem with we need to have enough critical mass of a supply chain to feed our composite base, especially if we're going to go into a large automotive supplier, or if there is an application in aerospace somewhere. We're not going to rely on a small volume of supply, so we need to have a critical mass. So we need these other areas to come with us, and that's where we'll also get innovation. So hempcrete uses the hurd or the shiv down the centre, and that mix that with lime, and you get one of the most thermally efficient concrete available today that also absorbs CO2 as it cures over 30 years. Biochar is quite interesting. Biochar is where you're basically charcoaling the plant and the fibre and the shiv, and that can be used for fertilizer, but potentially there's a use for that to go into things like graphene. Basically, you're creating a carbon structure. Potentially use that in graphene, which could then supplement material performance, or go into things like battery technology. We have biomass, which is maybe the parts of the plant which you don't use. The 10% waste can go into biomass, which can go into energy. The plant's also a source of lignin and cellulose, and a lot of research at the minute into, can we use lignin and cellulose? Can we use this plant as the base stock material for bioresins? Then we also look at the other benefits. So it's a local economic benefit. Sure. For any region that's going to adopt biomaterials as a supply chain and end users, that's a lot of income stream coming into probably quite diverse areas that are struggling into our more rural areas. And the other thing is biodiversity. When we think about industrial hemp, it actually contributes into the soil. So it locks in nitrogen, it breaks up the soil, and whenever you introduce that as part of a cycle within growing and agriculture, especially with potatoes, apparently, from speaking to hemp farmers, when they grow potatoes and hemp back to back, the hemp is better quality after the potato cycle, and the potato cycle is better after the hemp cycle. So there's a lot of biodiversity benefits for the soil, which is why farmers want to grow it here. So when we talk about natural fibre composites, we've tried to break it into 4 areas because they all have their different challenges. The first one's artisan composites. So this is more your artistic type composites. Could be your nice bathtubs for eco-friendly hotels. It's low volume, it's high value, it looks great. We don't need mechanical performance there. We can leave some of we don't need to have a clean fibre because that rustic look looks great. We're doing this today. There's companies doing this. The second one's semi-structural. So we're talking about GFRP replacement. Now this is more your short fibre, your half-inch glass fibre, not continuous. Things like your bathtubs, your standard GFRP, which you see is designed to say, right, we need 4 mil, and that's about the level of design that's needed into it, or we just need 4 ply. It's medium volume. It's low to medium value. You don't really need consistent properties of the product, but you do need stable supply chains. So that's the secondary. The third one is engineered composites. We're talking about where companies are going to design a product using FEA, using known material data sets and data cards. And for that, it's high volume. It's probably medium value. We're thinking about aerospace here in particular. but we need full mechanical data sets. It needs to be a low cost. We need to have significant supply chain stability. And we probably need an optimized supply chain there as well. We also need spinning capability, which we do not have in the UK. And the fourth area then is in the polymeric composites, which is, haven't seen too much in this. The volume is driven by end use. It can be low performance. It can be used as a filler, but there's a potential there to replace glass in certain scenarios with an injection molding. Then thermoplastic composites, continuous. There's other areas which could be developed using biocomposites. So what are we doing in this area? We've just got 5 minutes left. So first thing we did was we actually brought together the community. A conversation started just over a year ago where I had been out with our companies, fabricators of composites, who were telling me they want to make biocomposites, but they don't have a supply chain, but they've got the end applications. And the next day I was with a representative from the farming community who said farmers want to grow biocomposites, but they don't have an end use. And I told them the story where I'd been and said, very nice to meet you. I think we can solve this problem together. So we thought about creating a special interest group in Northern Ireland that's evolving constantly. But what we have is lots of pockets of the supply chain, whether it's from farming, weaving capabilities, fabricators, end users, all working in little pockets in isolation from each other. And they all want to collaborate because they see the bigger picture here. We managed to bring them together into a special interest group, so everyone now knows everybody, and we're going to tackle this as a regional ecosystem and spreading into mainland UK and into the Republic of Ireland as well. So we've been looking at developing that supply chain. Also looking at things like legislation, so working with the legislative bodies to make sure that we can have some freedom to do what we need to do. For example, if we want to grow seeds, you can't do that in Northern Ireland at the minute. At some point you will. Second area was around processing and fabrication. So enhancing the material performance through bioengineering and process optimization. There's short-term goals and there's long-term goals there. The short term, how do we just process biocomposites? How do we process natural fibers with bioresins? There's quirks in there, nuances which we need to overcome. One that I've discovered this week is how do we establish fiber void content on a natural fiber composite? Traditionally, we take a carbon fiber and epoxy, you put it through TGA, and you get the resin burns off and leaves the fiber. You calculate the volume. That works well whenever carbon burns at 1,000 degrees plus, but whenever your fiber burns at the same temperature as your resin system, we've now got a technology gap. Also looking at material format development in collaboration with other centres of excellence. So how do we take this into sheet moulding compound? How do we take this into thermoplastics, into injection moulding? We're looking at end-use applications. We want to demonstrate products, measure the life cycle analysis of products, create reliable mechanical data sets. That doesn't exist at the minute. We do not have a single baseline mechanical data set back to back where we can compare carbon, glass, and all the different types of natural fibers. That's something we're addressing this year. Trying for sustainability and looking at cost as well. But then we have the challenge of end of life. Doesn't make sense to recycle natural fiber composites that have a large negative CO2 hit. If you're just counting CO2, it doesn't, but do we still want to landfill these products? So we're looking at what are those end of life strategies, and not just within composites, and how does it complement into energy, into agricultural sector. So last slide, collaboration is key to grow this sector and optimize the product for manufacturing. We're looking at global collaborations. Yes, we're research based, we work together, but we all know that everybody competes. Everybody competes globally for the slice of the pie in research and development. But we're looking for global collaborations because biomaterials do not travel. The reason for using biomaterials is primarily to get your carbon footprint down. Doesn't make sense if you then put it on a ship and ship it 12,000 miles around the globe. you lose that opportunity. So we need to create centres where we grow, parts of the world where we grow biomaterials optimized for composites, and we need to collaborate with those areas. So, for example, with Spain, with India, with Canada, with the USA, we're looking for those global collaborations of people who are trying to do the same that we're trying to do, so we can all learn and all benefit. We need end-use applications, non-structural and semi-structural applications across multiple sectors. Biomaterials, I'm not going to be naive, it is not going to replace carbon fibre in a wing skin or a wing spar. It's not going to do that. But even within aerospace, is there non-structural, semi-structural applications, non-product applications, such as tooling, where we could replace this, could replace carbon fibre or glass with natural fibre products? We're looking at increased focused funding. It's probably a message no one from the UK government in this, but it's very hard to get focused funding which exactly fits this challenge and opportunity. It's something we're trying to fix. And we need scientific research. There's so many new technology gaps which we're discovering, as discovered today, with how do we just measure void content and how to measure fibre volume fraction using processes which are not designed for the materials which we're using. There's so much scientific research to be done across the global research community. So that just brings me to the end, and pass back to Julietta if we have time for any questions. I don't know how strict you are with your meeting endings.
Thank you so much for your presentation and for coming to talk in our committee meeting. So we'll take maybe one question from the audience. Romain, please go ahead.
Hi, Peter. Thank you very much. Very interesting subject and very interesting presentation. I also had the chance to visit NIAS during ICCM. It was great to see your center. My question is regarding natural fibers with thermoplastics. Typically, thermoplastics require higher temperature to be processed. Because I'm not really aware what's the maximum temperature fiber can sustain, and how does that limit their use with thermoplastic? And is there any treatment or things that can be done to the fiber to improve their resistance?
You've just given the title of probably several PhD studies that could be done there. Yes, it is a challenge. If we want to mix it with PPS and PEEK, we will have a challenge. There's a degradation temperature. I'm actually running a trial today on TGA to find on the sample of hemp that we're using what the exact, where that burn off point is, but it is in the high 100s, 200 Celsius. It is in that region. So compatibility with something like polypropylene and the low end polymers, I think is feasible. Putting it in with PEEK into an injection molding process of 400 degrees Celsius will have huge challenges. But is there, that's what we're here for. We're here to solve problems. We're scientists, we're researchers. How can we solve that problem through treatment? Keeping in mind, you can also use hemp to create biochar, which burns at 1,000 degrees in the absence of oxygen to create basically a charcoal. That is basically a source of graphene. So if you have a high doping of that within PEEK, what does that enhance the product? There's another two or three PhDs. There's a lot of research here to be done. There's so many challenges. But I think today we could mix it with low-end polymers without many problems.
Okay, thank you. Very interesting. Thank you very much.
Thank you for your question. Alberto, please go ahead.
Yeah, hello, Peter. Thank you very much for your presentation. That was fantastic. I just wanted to ask, when you mentioned that carbon fiber, or that is unlike that biocomposites would replace carbon fiber in an aircraft, etc. Are you within Belfast NIAS looking at things like producing that carbon fiber from a bio-based precursor such as lignin, cellulose, and then make it into carbon fiber, which could be middle of the road solution for that more structural application?
Yeah, I understand your question there, Alberto. So using fiber directly, no, I don't think that could be done, but you're right, using lignin as a source to make carbon fiber. There's been a lot of work done at the University of Limerick, or UCD. It's one of the universities down south have done a lot of work on that. So this is where I would turn to Ulster University, to Alistair Michael Hager and Eddie Archer. And their team, they are looking at that, and it would be in collaboration with other centres to try to understand how we can do that. I know there's other centres globally. There's a company in Canada, in the University of Calgary, who are using asphaltene, byproduct of the bitumen industry, to create carbon fibre. That's doing something very, very interesting there. Again, it's not bio, but it's not using our traditional sources of materials for carbon.
Yeah, thank you.
Thank you. And Eric, please go ahead.
Hi, thank you for the presentation. I posted a question in the chat as well. I'm very interested in that data set you talked about you're working on, comparing natural fibers, glass fibers, carbon fibers. How can I stay in the loop on that to get the results when that is completed?
Yes, so we're doing that work initially as part of our AMIC core projects. So that would be for access by members of the centre. But happy to chat to you offline if you get my email address somewhere. I'll type it in actually, and then everyone has it. If you want to touch base with myself, and we can talk a bit more about that as well. So
sure, thank you.
Thank you. And on that note, with your email, would you be okay if we include your email in the minutes of the meeting? If anyone else wants to contact you. Okay, perfect. And we have Michael as well. Please go ahead. You raised your hand.
Yeah, a quick question. I was wondering if you've looked at a basalt fiber reinforcement as a kind of like a replacement for like a glass fiber, because I know that's something that we've looked at, and I was just wondering if you looked at that, your thoughts on basalt fiber in general.
Yeah, we did a study that it was the same time we were looking at the different, using lignin for carbon fiber. Ulster University did a little bit of work into the basalt side of things. And with basalt, you still need to, you're taking it from rock. Yes, it's a natural source, but is it any different from glass, which is a natural source? You're still having to heat it up to 1,000 degrees plus to Celsius to be able to spin it. So is it a sustainable fiber? I don't know. I haven't been focused too much. It's not within my scope whenever I'm looking at biomaterials. I have used it before though in my previous job. I find it to be very effective in, compare glass to basalt. We were able to, just by changing some of the structure and changing some of the materials from glass over to basalt in certain parts, we were able to double the performance of the product for only a 10% increase in cost. So it has its uses, but it has its supply chain challenges as well. I think half the source comes from Ukraine, so it's a challenge, or has been a challenge in the last 2 years. So it's something. It's there. It was the big promise of being something big and different. It sort of hasn't followed through in the market, but it does have its niche applications.
Okay, great. Yeah, I was going to say that's pretty consistent with what we've found as well. It certainly performs, generally better than like an E-glass fiber, kind of up there with S-glass even. But yeah, supply chain issues it's an issue. So
yeah, at the time I was using it for that application. I was a huge fan of it at the time. I just haven't been looking at applications where where basalt would be relevant lately.
Okay, great. Well, thank you. I appreciate it.
Okay, thank you very much. So thank you again, Peter, for taking the time for preparing this presentation, coming to talk to the members of the Thermoplastic Committee. So with that, we will wrap this meeting up. So thank you so much, and we'll meet again in about a month. So thank you so much.